this section, we're going to be talking about Hamilton paths and circuits. So in the last section, we did Euler paths. And if you remember about Euler paths, we wanted to cover every edge. Okay? But now we're going to change our problem slightly. And where we're going to end up is solving what is called the traveling salesman problem. Okay? And if any of you work in sales or know someone who works in sales and they have to travel a lot, one of the things they want to do is to try to travel most efficiently. So in other words, cover the least amount of distance in their road trip, or if you're buying plane tickets, you want to find the cheapest route. So for example, here we have some local salesperson, and they have to go to Orlando, Tampa, Miami, and Bonifay. And they live in Orlando, so they want to start and end in Orlando. So the first thing they did is they went to AAA and they came up with a mileage chart. Okay, I could have also done this with airline prices, but it's all in the States, so I went ahead with mileage. Okay, and this is a typical mileage chart. Notice that from Orlando to Orlando, there's a dash because, well, there's no miles. And from Orlando to Tampa, it's 85 miles. From Orlando to Miami, it's 232 miles. From Orlando to Bonifay, it's 334 miles. If you're wondering where Bonifay is, it's up in the Panhandle. Beautiful little town. Okay, and the same on all of these. And this is what's called a mileage chart. Of course, the ones you look up are a whole lot bigger because they have a whole lot more cities. But I want to try to keep this simple. And the traveling salesman problem is find the shortest route starting and ending in Orlando that visits each other city once. Okay, so this salesman wants to go from Orlando, visit these 3 cities, and end up back in Orlando and travel the least amount of miles. Okay? Okay, so the first thing I'm going to do is I'm going to draw a graph representing Orlando, Tampa, Miami, and Bonifay, and the mileage in between. All right, so here's my graph. Notice I had 4 towns, Orlando, Tampa, Miami, and Bonifay. And I drew edges connecting all of the cities because we can travel to all of these cities. Okay, and I labeled each of the edges with the mileage. Okay. This is what's called a weighted graph. A weighted graph is a graph where each edge has a weight. In this case, the edge represents miles. You're also going to have examples where this is going to represent the price of the airline ticket between the two. Okay? And as you work through the homework, you'll see different examples. A complete graph just means that every vertice connects to all of the other vertices. Okay, so in other words, we can get from Tampa to Orlando to Miami and to Bonifay. Okay, and that's usually, we have to have a complete graph when we're working with a salesman problem. You can travel between all of the cities. A Hamilton path is a path that contains each vertex exactly one time. Okay, remember, when we did Euler paths, we had to visit every edge. In a Hamilton path, we don't have to visit every edge, but we do have to visit every vertex. Okay, so that's going to be something you're going to have to keep straight in your head. Euler, edges, all of them. Hamilton, vertices. And a Hamilton circuit is a path that begins and ends at the same vertex and passes through all other vertices of a graph exactly one time. Okay? So like in our traveling salesman problem, we want to visit all of the cities. We don't have to travel all of the roads connecting all the cities. We just have to get to each city once. And we want a circuit because we want to end up back in Orlando. Okay, so here's my first example. And I want to find a Hamilton path in this picture here. So in other words, I want to travel through every vertice once. I don't have to get back to the vertice I started with. And remember that I don't have to go through every edge. I just have to travel through every vertice. Okay? All right, so Hamilton path can start anywhere. They didn't tell me where to start, so I'm randomly going to start at B. Okay? From B, let's go to G and pick up G. From G, let's go and pick up F, and I'm randomly going through this picture. You're probably not going to pick the same path I do. From F, let's go to I. From I, let's go to E. From E, let's go to H. From H, let's go to D. D to C. C to A. Notice I have visited every vertex. Okay? They've all been visited. Did I cover every edge? No, but that doesn't matter because I am doing a Hamilton path. Okay? And like I said, that's not the only Hamilton path, but that's the one I came up with. Okay? Let's find a Hamilton circuit in this guy. Okay, so remember, in a circuit, we have to begin and end at the same place. Okay, let's start with A. That's a good place to start. That way we can remember. Let's make this easy. Let's go from A to B to C to D. Okay, so from A to B to C to D. Now from D, let's go down to H. Let's go to L. Okay. From L, well, there's only one way to go, which is to K. From K, let's go up to G. G, notice that the only place to go now is F, because F hasn't been visited. J. I. E. And remember, this is a circuit, so I have to go back to where I started, back to A. So in a circuit, you have to begin and end at the same place. All right, so here's a little tidbit. How many Hamilton circuits are there in a complete graph? Well, if we have a small graph with a little number of vertices, we're good. Once we have a lot of vertices, it can get out of control. And there's a little formula for figuring out how to do this. If you have n vertices, you're going to have this many Hamilton circuits. Now, what does this mean? That doesn't mean n-1. No. This in math is called n-1 factorial. So this little guy is called factorial. Okay? If you've taken 1106, you ran into this when we were doing counting elements and sets, okay, and combinations and permutations. Okay, so let's say we have 6 vertices. Okay, if we have 6 vertices, we're going to have 6 minus 1, which is 5 factorial circuits. Okay, so what is 5 factorial? Okay, factorial. All right, it's pretty easy. Start with the number that's given, which is 5, times the next number under it, times the next number under it, until you get to 1. Okay? So 5 factorial is really 5 times 4 times 3 times 2 times 1. Now, this is some pretty easy math to do, right? 5 times 4 is 20, 2 times 3 is 6, and that's 120. So if you have 6 vertices, you can come up with 120 different circuits. Okay, I am not going to have you come up with 120 circuits. We have better things to do with our time. Okay? Let's say you had 4 vertices. All right, we're going to have 4 minus 1, which is 3 factorial. 3, count down. Oh, so if you have 4 vertices, you're only going to have 6 Hamiltonian circuits. Okay, so in our example with our traveling salesman, there are only 6 circuits that I have to look at.